Imagine you're sitting in a commercial airliner.
Okay.
You're cruising at 35,000 feet,
Right.
and the air outside is minus 50 degrees Celsius, which is, cold enough to freeze exposed skin in minutes.
Oh, absolutely. It's a brutal environment.
Yeah. And the wings outside your window are just being bent upward by aerodynamic forces that they could snap a steel bridge in half, and you are essentially sitting on top of tens of thousands of gallons of highly flammable jet fuel.
Right. Just casually sipping a coffee.
Exactly. Sipping coffee, watching a movie. We tend to look at airplanes as just these rigid, static tubes of metal. But today we're doing a deep dive into the invisible, dynamic ecosystem that's actively fighting the laws of physics to keep you alive up there.
It really is a battle against the environment.
Yeah.
And it's managed by this incredibly intricate web of interconnected systems. You cannot change a single input on an aircraft without the entire organism reacting in some way.
And that is exactly what we are unpacking today. We're taking a comprehensive journey through aircraft general knowledge, specifically tailored for the ATPL, the Airline Transport Pilot License.
Right, pulling directly from the official exam study materials.
Exactly. Airframes, hydraulics, electrics, power plants, survival systems. We are going to mentally build this airplane on the tarmac, power it up, and fly it into that freezing upper atmosphere.
I love that. And the goal here isn't just to help you, memorize rote facts for an exam.
Exactly.
It's how to help you understand the fundamental physical realities, the why and the how behind the machinery.
Which is the only way to truly master the ATPL, right?
Oh, 100%. The examiners do not want pilots who just memorize flashcards. They write questions specifically designed to trap you if you don't understand the underlying mechanics of how these systems integrate under stress.
So let's start right on the tarmac. Before we can wire the computers or start the engines, we need a structure. We need a skeleton and a skin.
Right, the airframe.
Yeah, let's talk about the fuselage. I think a lot of people intuitively picture an airplane as just a hollow tube, and there's a specific engineering term for that, right? Monocoque?
Yes, monocoque. Think of a standard aluminum soda can.
Okay.
In a true monocoque structure, the skin itself takes all of the structural load. It is usually made of aluminum or magnesium alloys. And aside from some internal former rings that just give the tube its aerodynamic shape, there's no internal load-bearing skeleton. The skin does all the heavy lifting.
Which sounds incredibly efficient for weight savings.
Yeah.
And here's the catch. If I'm designing an airliner and I need to cut a massive 8-foot cargo door into the side of my soda can, what happens?
Well, the whole thing loses its integrity. If you take a soda can and poke a large hole in the side, you can crush it with 2 fingers.
Oh, wow. Yeah.
The moment you compromise the skin in a monocoque design, you compromise the entire aircraft. Because transport category aircraft require massive cargo doors, passenger doors, and rows of windows. True monocoque is virtually impossible to use for airliners.
So that brings us to the modern standard, which is the semi-monocoque design.
Exactly.
So if monocoque is a hollow soda can, semi-monocoque is more like a human rib cage, right? Where the bones and the skin are sharing the work.
That's a very apt way to visualize it. The skin still carries a portion of the aerodynamic load, but it is heavily supported by an internal skeleton. First, you have frames.
Okay, what do those do?
They run vertically around the circumference of the tube, handling vertical stress and giving the fuselage its rigidity. Then you have the main heavy-duty structural members called longerons.
So the longerons are like the spine.
Correct. They run lengthwise from nose to tail, handling the massive longitudinal stresses of flight.
Right.
And to bridge the gaps between the frames and the longerons, and to support the skin panels so they don't buckle, you use thinner lengthwise beams called stringers.
Okay, stringers.
Finally, at the front and back of the pressurized cabin, you cap this whole structure off with bulkheads. These are heavy pressure seals that make the structure airtight so we can, pump it full of breathable air later on.
It's an entire team of structural members. And the materials we use to build this team are heavily tested on the ATPL. The sources specifically highlight the difference between composite structures and sandwich construction.
Yeah, that's a key distinction.
What are we looking at there?
Let's look at composite structures first. A composite is essentially a combination of 2 materials, a matrix, which is like a resin or glue, and fibers, like carbon or glass, embedded within it.
Right.
The absolute engineering brilliance of a composite is that its strength is directional. If you have an aluminum block, it's generally equally strong in every direction.
But with a composite.
With a composite, engineers can align the fibers to perfectly match the direction of the expected aerodynamic load.
Meaning you don't waste weight making a part strong in a direction that never actually experiences any stress.
Precisely. That's why they offer such an incredibly high strength-to-weight ratio. Now, contrast that with sandwich construction.
Yep.
This is exactly what it sounds like. You take two very thin, strong outer sheets and separate them with a very light core material, often shaped like a honeycomb.
So you get something that is very stiff, but weighs almost nothing. But there's a trap here for the exam, right? Because it's full of empty space inside.
Yes. Because the core is so light and mostly air, sandwich construction is entirely unsuitable for absorbing concentrated loads.
Nah.
You would use it for floor panels or maybe a control surface, but you would never bolt a 5-ton jet engine directly to a sandwich panel. It would crush the honeycomb core instantly.
That makes total sense. So we have our fuselage built. Let's attach the wings. Most modern airliners use a cantilever wing design.
Right.
That means they are attached only at the wing root where the wing meets the fuselage. There are no external struts or support wires running out to the middle of the wing like you'd see on an old biplane.
And because the entire span of the wing is supported by just that one attachment point at the root, the bending moments, the mechanical leverage trying to snap the wing off are absolutely massive right at the side of the fuselage.
Wow, yeah.
To prevent the wing from folding, engineers rely on the torsion box.
What does that actually look like inside the wing?
Well, if you slice a wing open, the torsion box is the main structural center. It is a box made up of spars running lengthwise, ribs running chordwise from front to back, the thick upper and lower wing skin, and stringers.
Okay.
But the hero of this box is the main spar. It often looks like a giant steel or aluminum I-beam. It has a vertical web and horizontal caps called girders, and it bears the vast majority of the aerodynamic lifting load.
But those loads are constantly changing. The sources point out that the stress on the wings completely flips depending on whether the plane is flying or parked on the ground.
Yes, let's visualize the physics here. When you're parked at the gate, gravity is in charge. You have massive engines bolted to the wings, and the wings are full of heavy fuel. All that weight pulls the wingtips downward. When the wing bends down, the metal on the upper surface is being stretched out. It is in tension. The metal on the lower surface is being squeezed together. It is in compression.
Okay, I see. But the moment the wheels leave the runway, the physics reverse. Lift is now pushing up from underneath the wing, carrying the entire weight of the airplane, bending the wingtips up toward the sky.
Exactly. The forces completely flip. In flight, the upper surface of the wing is now being squeezed together in compression, while the lower surface is being stretched out in tension. The ATPL examiners love to test your spatial awareness on this exact reversal.
So if I'm the pilot and my wings are bending violently upward in flight, putting massive stress on that wing root, how do I manage that? I mean, I can't just change the metal.
No, you manage it through operational procedures and system design. First, modern aircraft can utilize upfloat ailerons.
Upfloat ailerons?
Yeah, during cruise flight, the computers rig both ailerons to angle slightly upward. This dumps a bit of lift out near the wingtips and shifts the center of lift further inboard, closer to the fuselage.
Oh, that is clever.
By moving the lifting force closer to the attachment point, you reduce the mechanical leverage, decreasing the bending moment at the root.
But there's also a trick pilots use with the fuel, right?
Yes, and this is highly testable. You use the fuel as a physical counterweight. An aircraft usually has fuel tanks in the center fuselage and out in the wings. You always burn the fuel in the fuselage tanks first.
Wait, why the fuselage first?
Because you want to keep the heavy fuel out in the wings for as long as possible. The physical weight of that fuel pushes down against the aerodynamic lift pushing up. It acts as a structural relief for the wing root.
So the fuel is literally holding the wings down while the air pushes them up. Brilliant. All right, so we've got a skeleton, we've got a skin, but sitting on the tarmac, it's totally paralyzed.
Right.
If I want to move those massive control surfaces on the wings and the tail against a 500-mile-an-hour headwind, human muscle isn't going to cut it. We need hydraulics.
Hydraulics rely on a very simple piece of physics called Pascal's law, which states that pressure applied to an enclosed fluid is transmitted undiminished in all directions. The formula you need is pressure equals force divided by area.
Okay, P equals F over A.
Exactly. In aviation, we have a dilemma. We need an enormous amount of mechanical power to move those flight controls, but we have strict weight limits. How do you get high power with low mass?
The sources are clear on this. You use a high-pressure system with a low volume flow. Specifically, transport category hydraulics operate at a staggering 3,000 psi.
Right. That extreme pressure allows the hydraulic actuators to be physically smaller and lighter while still outputting incredible force. But pushing fluid at 3,000 psi generates massive heat and stress. The fluid itself is critical.
Right. Yeah.
You will commonly see a fluid called Skydrol used in large airliners. It is a purple phosphate ester-based fluid. Its primary advantage is that it is highly fire-resistant.
But the outline also mentions synthetic oils. Why use those over Skydrol?
Synthetic oils offer the highest resistance against a phenomena called cavitation.
Cavitation, what's that?
When a pump tries to pull fluid faster than the fluid can flow into it, it creates a localized area of extreme low pressure. This causes the fluid to actually boil at room temperature, forming vapor bubbles.
Boiling at room temperature. Wow.
Yeah, and when those bubbles hit the high-pressure side of the pump, they collapse violently. This microimplosion can literally tear chunks of metal out of the pump and destroy it. Synthetic oils resist that bubble formation better than anything else.
Okay, so we have this 3,000 psi muscle. Let's hook it up to the pilot's yoke in the cockpit. The exam breaks flight controls down into 3 historical categories: manual, power-assisted, and powered, which is also known as irreversible. Break those down for us.
Manual controls are what you find on a Cessna. Steel cables run directly from the pilot's yoke all the way back to the elevator or rudder. It is a direct mechanical linkage. It is reversible, meaning if a strong gust of wind hits the rudder while you're parked on the ground, the force travels back through the cables and violently spins the pedals in the cockpit.
Which is why manual aircraft require a physical gust lock on the ground. Otherwise, the wind will slam the control surfaces against their hinges and damage them.
Exactly. Now, as airplanes got bigger and faster, pilots physically couldn't pull the yoke hard enough. So engineers introduced power-assisted controls. You still have a direct mechanical cable linking the yoke to the surface, but now a hydraulic actuator helps you push.
So it's effectively power steering.
Yes. And it is still reversible, so you still feel the aerodynamic forces pushing back against your hands.
But when we get to modern, large transport aircraft, the kind you need an ATPL to fly, we move to completely powered or irreversible systems.
Right.
Here, there is no physical cable pushing the surface. The pilot moves the yoke, which opens a valve, and 3,000 psi of hydraulic fluid does 100% of the heavy lifting via servo motors.
And the term irreversible is the key here. The force only goes one way. If a gust of wind tries to push the rudder on an airliner, the aerodynamic load hits the hydraulic fluid inside the actuator. Because liquid cannot be compressed, a hydraulic lock occurs. The fluid acts like a solid steel wall. The wind cannot move the surface, and that force cannot travel back to the cockpit.
So no gust locks are needed on an airliner. But hold on, if the system is irreversible and no force can push back, that means when I pull back on the yoke at 400 knots, I feel zero physical resistance from the air outside. That sounds terrifying.
It is.
If pulling back feels as light as a feather, I could accidentally snap the airplane in half with one aggressive jerk of the wrist.
You've just identified a massive vulnerability, and the engineering solution to this is called the Q-feel system, or artificial feel. Because the hydraulic system robs the pilot of natural aerodynamic feedback, Q-feel is absolutely non-negotiable for safety.
How does it fake the feeling of the wind?
It uses air data. Q is the symbol for dynamic pressure, the physical force of the air ramming into the front of the aircraft. As your airspeed increases, dynamic pressure increases.
Okay.
The Q-feel system takes that data and uses a secondary hydraulic actuator on the control column to artificially stiffen the yoke. The faster you fly, the harder it physically is to pull the yoke back, preventing you from overstressing the airframe.
So what happens if the Q-feel system fails?
It's an emergency. If it fails, the controls will revert to their base state, dangerously light at all speeds. You'd have to fly with literal fingertips to avoid breaking the airplane.
Wow. So in a manual system, when I want to trim the aircraft to relieve pressure on the yoke, I turn a wheel that physically moves a tiny trim tab on the elevator. But in this irreversible hydraulic system with Q-feel, what is the trim actually doing?
This is a classic exam trap.
Yeah.
In a fully powered, irreversible system, trimming does not move a tab on the surface. Trimming simply adjusts the zero force point of the artificial feel system itself.
Oh, I see.
You are just telling the computer, hey, shift the neutral center point of the artificial stiffness to right here. The physical control surface moves, but you aren't fighting the wind with a tab. You're just resetting the Q-feel computer's baseline.
Speaking of computers, fly-by-wire takes this one step further. There are no cables opening hydraulic valves. The pilot's yoke is essentially a joystick, Inputs are converted into electrical analog signals, sent down wires to a computer, which then commands the hydraulic actuators.
Exactly. And the fail-safe here, if the computers completely lose their minds, is called direct mode, where the electronic limits are removed and the stick directly commands the valves.
And we must talk about the rudder limits in these high-speed systems. The rudder is a massive vertical barn door. If you were to fully deflect it at high indicated airspeeds, the lateral aerodynamic force would instantly tear the vertical stabilizer off the fuselage.
Absolutely.
So how do we stop the pilot from doing that?
Two main limiters you need to know. First is the rudder ratio changer. As airspeed increases, this mechanism physically changes the mechanical advantage. For the exact same amount of foot pedal movement by the pilot, the actual rudder surface back on the tail deflects less and less.
And the second one?
The variable stop system. This is more restrictive. As speed increases, it physically blocks the pilot from pushing the pedals all the way to the floor and simultaneously limits the maximum travel of the rudder surface itself.
Okay, so we've got the muscles hooked up. But to send those analog signals in a fly-by-wire system, or just to power the hydraulic pumps, we need a nervous system. That brings us to basic DC electrics and wiring. Let's drill down to the absolute atomic basics.
Sure. At the center of an atom, you have positive protons. Orbiting them are negative electrons. Normally, they balance out to a neutral charge.
Right.
But if we introduce friction, heat, or a chemical reaction, a process called ionization, we can strip electrons away. The atom is no longer balanced. It has a net charge.
And the material's ability to let those freed electrons flow depends on its outer shell, the valence electrons.
Exactly.
The sources state if a material has only 1 or 2 valence electrons, it gives them up easily. It's a conductor, like copper. If it has a full shell, like 8, it holds on tight. It's an insulator, like rubber. And if it has around 4, it is a semiconductor.
Exactly right. And when those electrons break free and move down a wire, that is electrical current. Now, there is a historical trap here for exam takers.
Oh, what's that?
In reality, actual electron flow moves from the negative terminal to the positive terminal.
Yeah.
However, the pioneers of electricity guessed wrong hundreds of years ago. So, conventional flow, which almost all aviation schematics, rules, and diagrams are based on, assumes current flows from positive to negative.
Good to know for diagram questions. Now, we measure this flow in amperes or amps. The ATPL formula here is current, denoted by the letter I, equals coulombs divided by time in seconds. Now, a coulomb is just a measurement of quantity. It is a massive block of electrons, specifically 6.25 times 10 to the 18th power electrons. So 1 ampere means 1 coulomb of electrons is walking past a point in the wire every single second.
But electrons don't just move on their own. They have to be pushed. That push is the electrical force, the electromotive force, or EMF, measured in volts. We often call it potential difference.
Let me try a mechanical analogy here, tying back to what we just talked about. We can look at electricity exactly like the hydraulic system we just built.
Yes.
The volts, the potential difference is like the 3,000 psi of pressure sitting in the hydraulic pump.
Yes.
The pressure is always there, pushing hard against the valve, even if the valve is closed. Current, the amps, is the actual flow rate of the liquid when you open the valve.
That is an excellent way to visualize it. And just as you would use a pressure gauge to tap into a hydraulic line without blocking the flow, use a voltmeter to measure EMF. The sources are very specific on this operational rule. A voltmeter must be connected in parallel across a component, and it must have an exceptionally high internal resistance.
Why high resistance?
Because if it had low resistance, the current would take the path of least resistance right through the meter, bypassing the component and causing a short circuit.
Which brings us perfectly to resistance itself, the friction in the wire. Specific resistance is always measured at a baseline of 0 degrees Celsius, so engineers can standardize and compare different materials. And the exact opposite of resistance is conductance. It's just a reciprocal mathematical value.
The critical concept for the exam is how temperature affects resistance. We have two behaviors. A positive temperature coefficient, or PTC, means that as a material heats up, its resistance increases. This is the behavior of almost all normal conductors, like the copper wiring in the aircraft.
But negative temperature coefficient, an NTC, means that as the temperature rises, the resistance actually decreases. And this is characteristic of insulators and semiconductors.
Keep NTC in mind because it becomes incredibly dangerous later when we talk about aircraft batteries. But first, let's look at the rules of the circuit. Ohm's law gives us the relationship voltage equals current multiplied by resistance.
V equals I times R.
Right. But to analyze a complex aircraft wiring schematic, you need Kirchhoff's laws.
Let's break those down.
Kirchhoff's first law is about current. It states that the sum of all currents entering a junction in a wire must equal the sum of the currents exiting that junction. Think of a plumbing T-junction. If 2 gallons a minute go in, 2 gallons a minute must come out the other sides. Electrons don't just vanish.
Makes sense.
Kirchhoff's second law is about voltage. In any closed circuit loop, the sum of all the voltage drops across the various components must equal the total voltage supplied by the battery.
And if we are adding components resistors to this circuit, how we wire them changes the math completely. If I wire resistors in series, daisy chaining them one after the other on a single wire, I just add the resistance together, R1 plus R2 plus R3, the total resistance goes up.
Right. But if you wire them in parallel, meaning the wire branches off into multiple separate paths, each with its own resistor, and then recombines, the formula is 1 over total resistance equals 1 over R1 plus 1 over R2, and so on.
Which mathematically means that adding more resistors in parallel actually lowers the total resistance of the entire circuit.
Yeah, exactly.
That seems counterintuitive until you realize that by adding parallel paths, you are giving the electrons more lanes on the highway to travel down, reducing the overall traffic jam.
Exactly. Now, there's a specific circuit arrangement you must know called the Wheatstone bridge. ATARS is used to measure an unknown electrical resistance with extreme precision by balancing 2 legs of a bridge circuit, one of which includes the unknown component.
How do you know when it's perfectly balanced?
There is a highly sensitive ammeter placed across the middle of the bridge called a galvanometer. The exam question will likely ask what this meter shows when the bridge is balanced. The answer is exactly 0. When the voltage ratios on both legs are equal, no current flows across the middle bridge.
Okay, and the final piece of the basic math. Power, measured in watts, is just voltage multiplied by current. P equals V times I. So we understand the physics of the wire. How do we physically string those miles of wire through the airliner? The outline lists 2 methods, dipole and unipole.
Dipole is a 2-wire system. You have one wire taking power from the battery out to the landing gear light, and a second wire returning from the light back to the battery to complete the circuit. This is mandatory in aircraft made of composite or non-metallic materials because you physically need that return wire.
But the sources say almost all commercial transport aircraft use the unipole system, also known as a single pole or earth return system.
They do.
This means we run one wire out to the light, and for the return path, we just attach a wire from the light directly to the metal aluminum skin of the airplane. The entire fuselage is the return wire, and this earth reference is always considered to be 0 volts.
That's correct.
I have to push back here. We just established that electricity is trying to flow back to the battery. If we are using the entire metal skin of the airplane, the floor I'm standing on, as a live return wire, aren't we just begging for a massive, catastrophic short circuit? If one single live wire frays and touches a frame, it skips the load completely.
You've hit on the exact engineering trade-off.
Yeah.
Yes, the risk of a short circuit is significantly higher in a unipole system. A short circuit happens when the load is bypassed, meaning the resistance drops to almost 0.
Right.
According to Ohm's law, if resistance drops to 0, the current spikes to an infinite massive surge, which creates Benz heat and instantly starts an electrical fire.
So why on earth do we use it in a jet carrying 300 people?
Because the weight savings are staggering. By eliminating the return wire for every single electrical component on the aircraft, you save thousands of pounds of copper wire. Furthermore, because the entire aluminum fuselage is so massive, its cross-sectional area is huge, which means the electrical resistance of the return path is practically 0.
Wow, okay.
It's incredibly efficient. And, from a maintenance perspective, it's much easier to trace one broken wire than 2.
So we accept the risk of catastrophic short circuits to save weight, which means our internal defenses better be flawless. Let's move into electrical protections, static, and AC power. What is the first line of defense against that massive current surge?
Fuses. They are simple, sacrificial components. A fuse is just a thin wire filament inside a glass or ceramic tube placed in series with the circuit. They are rated in amps. If the current exceeds that rating, say, during a short circuit the filament gets too hot, physically melts, and breaks the circuit, stopping the flow.
The regulations for the ATPL are very clear here. Pilots must carry spare fuses on board, specifically 10% of the total number of fuses, with a minimum of 3 for each specific amp rating.
But fuses are fragile and sometimes blow just from a momentary spike in current that isn't actually a fire hazard. For heavy-duty circuits like the main electrical bus bars that distribute power from the generators, we use circuit limiters.
How are those different?
These are slow-blow devices. They will allow a massive high-transient load to pass through, for instance, the huge surge of amps required for the first second of starting an electric motor.
Right.
And they will only break if that high overload is continuous.
But the most common protection pilots interact with in the cockpit are circuit breakers or CBs. Unlike a fuse that melts and is destroyed, a CB can be reset.
Right. And there are two main types you must differentiate for the exam. The magnetic CB uses an internal electromagnet. If a massive surge of current hits, the magnetic field instantly becomes strong enough to physically pull a latch, springing the breaker open. It reacts immediately and does not rely on heat.
Contrast that with a thermal CB, which uses a bimetallic strip. Two different metals fused together that expand at different rates when heated. Because it takes time for an overcurrent to physically heat the metal up enough to bend it and trip the latch, a thermal CB has a delayed response.
Yes.
It is designed to protect wiring against prolonged overcurrents that would eventually melt the insulation.
Operationally, the rules for resetting a tripped CB in flight are incredibly strict. If a breaker pops on the panel, you will see a white band on the stem indicating it's open. The rule is, you only ever attempt to reset a breaker if that specific system is absolutely necessary for the safe continuation of the flight and landing.
And even then, you only try to reset it once. If it pops again, you have a hard short circuit, and forcing it closed will start a fire. Which leads into a very specific design feature the examiners will ask about: the trip-free circuit breaker.
A trip-free CB contains a secondary internal contact mechanism. It means that even if a pilot physically holds their finger down on the breaker button, forcing it flush with the panel, if a short circuit still exists, the internal mechanism will still trip and permanently cut the power. You cannot force it to stay connected against a fault.
Whereas a non-trip-free CB can be held closed manually, and doing so in an aircraft is a great way to burn it down. Okay, so those are internal electrical threats. Let's talk about the sky outside. The outline brings up the triboelectric effect.
Right. The triboelectric effect is the buildup of severe static electricity on the surface of the aircraft caused by physical friction. As the jet pushes through the atmosphere at hundreds of miles an hour, especially in very dry, low-humidity air, or when flying through ice crystals and dust, friction literally strips electrons off the air molecules and deposits them onto the aluminum skin, creating a massive static charge.
This charge gets so intense it can cause actual sparks, pitting and burning on the metal, and it wreaks havoc on the communication radios. Sometimes you even see a visible glowing purple plasma on the windshield at night, St. Elmo's fire. So, how do we neutralize a plane that has charged itself up to 1,000,000 volts?
The first step is bonding. We must ensure the aircraft acts as a single, unified electrical mass. Bonding strips are thick braided metal cables that physically connect every isolated metallic part of the airplane. Together, the ailerons to the wings to the fuselage, the engines to the pylons.
By tying everything together, you turn the entire airplane into a giant Faraday cage.
Exactly. Bonding ensures there is a zero voltage difference between any 2 points on the aircraft. If the wing was at 1,000,000 volts and the aileron was at 0, the charge would arc across the hinge, causing a massive spark, destroying the bearing, and potentially igniting fuel vapors.
Wow. Yeah.
Furthermore, bonding ensures that if the aircraft is struck by lightning, the massive electrical energy can flow smoothly across the skin and exit the tail without penetrating into the fuel tanks or computers.
But even with bonding, the plane as a whole is still charged up like a giant capacitor. We have to bleed that static off before we land, otherwise the first ground crew member to touch the plane is going to get vaporized. To do this, we use static discharge wicks.
You'll see these looking like little antennas trailing on the back edges of the wings and the tail. The physics principle here is that electrical charge naturally concentrates at sharp points with minimal radius. By providing these sharp wicks, we allow the static charge to concentrate and quietly bleed off into the atmosphere through a controlled corona discharge. This prevents random violent sparks and keeps radio interference to an absolute minimum.
Okay, let's talk about where we store power onboard batteries. The sources divide these into primary and secondary cells. Primary cells are non-rechargeable. They are basically heavy-duty versions of AA batteries. We use them for isolated systems like emergency floor lighting, and they only need to provide power for about 10 minutes.
The main focus for the ATPL, however, are the secondary cells. These are the large, rechargeable aircraft batteries. In an emergency, if you lose all generators, these secondary batteries are legally required to provide critical electrical power for a minimum of 30 minutes.
We measure their capacity in ampere hours, or
Yeah.
it's a measurement of the total energy bucket, and it depends on the physical size and number of plates inside the battery. And importantly for maintenance, the actual real-world capacity of these batteries must be physically checked every 3 months.
You must know the two main chemical compositions used in aviation. The first is the traditional lead-acid battery. As it discharges, it leaves lead sulfate deposits on the plates.
And the exam loves asking about fluid spills. If you spill the highly acidic electrolyte from a lead-acid battery, you must neutralize it by cleaning it up with bicarbonate of soda.
Right. To charge a lead-acid battery, engineers use a constant voltage method. But it has a fatal flaw for aviation. Inside a 24-volt battery, you have 12 2-volt cells wired in series. Because they are in series, if a single cell physically breaks or dries out, the circuit is broken, and the entire battery instantly becomes unserviceable.
Which is a major reason why modern aviation relies heavily on alkaline or NiCad nickel-cadmium batteries. Their deposits are cadmium and nickel hydroxide. And if you spill this electrolyte, it is highly alkaline, so you must neutralize it with boric acid. Don't mix those up on the test. Lead acid gets bicarb, NiCad gets boric acid.
NiCads are charged differently, too. They use a pulse charging method, which is much faster. They are superior because they are physically lighter, they operate efficiently across a much wider temperature range, and critically, their voltage output stays incredibly flat and stable for a very long time before rapidly dropping off a cliff right at the end of their charge.
But NiCads have a dark side. They suffer from a memory effect if not deeply discharged regularly. More terrifyingly, they are susceptible to a catastrophic chain reaction called thermal runaway.
Yes, this is where that NTC, negative temperature coefficient concept from earlier, returns with a vengeance. Remember, an NTC means as temperature goes up, electrical resistance goes down. The internal separator material in a NiCad battery acts like an NTC.
Let's walk through the stampede. If a NiCad battery is being charged quickly, it gets hot. Because of the NTC, as the battery gets hotter, its internal resistance drops.
And according to Ohm's law, if the resistance drops while the charging voltage remains constant, the battery will pull more current from the charger.
Pulling more current generates even more heat, which drops the resistance even further, which pulls even more current. It's a runaway train. The hotter it gets, the faster it pulls power, until the internal electrolyte literally boils, venting toxic gas, melting the casing, and sparking an unstoppable chemical fire.
It's incredibly dangerous. To prevent this disaster, aircraft are equipped with a battery control unit, or BCU. The BCU constantly monitors the temperature of the battery. If it senses the temperature ramping up abnormally, or if it senses the battery is fully charged, it will physically isolate the battery from the charging bus.
Okay, good.
Additionally, the battery compartment requires heavy venting to the outside atmosphere to remove the highly volatile hydrogen gas that is naturally produced during charging.
All right, we've spent a lot of time on DC power direct current. Let's touch on the heavy lifting AC electrics, or alternating current, generated directly by the engines. Most aircraft generate three-phase AC power. Now, when wiring an AC generator, you have two choices: a delta connection shaped like a triangle or a star connection shaped like a Y.
Delta uses 3 wires and is physically lighter, but aviation universally requires the star method, which uses 4 wires.
Wait, if we are so obsessed with saving weight that we use the aluminum skin for DC return, why add a 4th wire for AC?
Because of the physical reality of an airplane. A building on Earth can ground its electrical systems by driving a copper rod deep into the literal dirt. An aircraft at 35,000 feet cannot.
Ah, right.
The star configuration takes the 3 phases and connects them at a central point, creating a neutral line, the 4th wire. This neutral wire acts as a floating sink, a place to safely absorb and balance out any excessive or unbalanced current between the phases. Without a physical Earth, the star connection is the only safe way to manage high-voltage AC.
Standard figures to memorize for the ATPL aircraft AC systems run at a phase voltage of 115 volts and a line voltage of 200 volts. But the frequency is the weird part. Wall outlets in a house run at 50 or 60 hertz. Aircraft run at 400 hertz. Why spin it so fast?
Again, it comes down to weight. Electromagnetic physics dictate that by running an AC system at a much higher frequency, the heavy iron cores inside electrical transformers and AC motors can be made significantly smaller and lighter while producing the exact same amount of mechanical power. Running at 400 hertz saves hundreds of pounds of iron across a large aircraft.
There is also a classic mnemonic you must know for how AC circuits behave: civil, CIVIL.
It describes the phase shift between voltage and current. In a capacitor, denoted by C, the current I, leads the voltage, V, hence CIV. In an inductor, denoted by L, the voltage V, leads the current I, hence VIL. Put it together, civil.
To control this AC power and convert it back to DC for the computers, we use semiconductors like diodes, which act as a one-way check valve, allowing electricity to flow in only one direction. And specifically, a Zener diode is used for voltage stabilization, clipping off harmful spikes. Okay, we've built the structure, hooked up the hydraulic muscles, and run the electrical nervous system. It is time to start the engines. Section 5, the heart, power plants.
Before we start burning fuel, we must define the physical rules of the air we are compressing, the gas laws. First is Boyle's law. It assumes a constant temperature. It states that the pressure of a gas is inversely proportional to its volume. The formula is P1 times V1 equals P2 times V2. If you take a cylinder of air and smash the piston down to halve the volume, the pressure inside doubles.
If I'm studying this, I remember Boyle's law starts with a B, and water boils at a constant temperature, so Boyle equals constant temp.
What about Charles's law?
Charles's law allows temperature to vary. It has two parts. If pressure is held constant, volume and temperature are directly proportional. V1 over T1 equals V2 over T2. Heat the gas, it expands.
Right.
If volume is held constant, like inside a rigid steel tank, pressure and temperature are directly proportional. P1 over T1 equals P2 over T2. Heat the tank, the pressure skyrockets.
Let's see. These laws violently applied inside a piston engine, which uses the Otto cycle. This is a four-stroke process. Every pilot learns it as suck, squeeze, bang, blow. Let's get technical. Stroke 1 is induction, the suck. The intake valve opens and the piston moves down the cylinder. This increases the internal volume. According to Boyle's law, increasing volume drops the pressure. Because the pressure inside is now lower than the atmospheric pressure outside, the outside air forcefully pushes the fuel and air mixture into the cylinder.
Stroke 2, compression, the squeeze. The intake valve closes. The piston moves rapidly back up, shrinking the volume. Pressure and temperature skyrocket. The outline notes this is an adiabatic process. What does that massive word mean in reality?
Adiabatic means the compression happens so blisteringly fast that there's no time for the heat being generated to escape through the metal cylinder walls to the outside environment. All the heat energy stays trapped in the gas. The text also notes it is ideally isochoric, which means constant volume.
Wait, how can it be constant volume if the piston is actively moving up and crushing the gas?
Well, the isochoric part refers theoretically to the exact moment of combustion. In a perfect theoretical Otto cycle, the spark plug fires and the entire fuel mixture explodes instantaneously, exactly as the piston reaches top dead center.
Oh, I see.
Yeah, for that microsecond of explosion, the piston hasn't started moving down yet, so the volume is technically constant while pressure goes infinite. In reality, it takes time for the flame front to burn, so the volume does change. But the ATPL asks about the ideal cycle.
Stroke 3 is power, the bang. We ignite the spark plug just before top dead center to give that flame front time to propagate. The explosion generates massive pressure, driving the piston down. And finally, stroke 4, exhaust, the blow. The exhaust valve opens, the piston sweeps back up, pushing the burnt, useless gas out.
Mechanically, the pistons are moving straight up and down. This reciprocating motion is converted into spinning rotary motion by the heavy crankshaft. Because each piston only fires once every 4 strokes, the crankshaft actually spins at exactly twice the speed of the camshaft, which is the rod geared to open and close the valves.
And when we measure the power this engine makes, it is simply torque the twisting force multiplied by the RPM. Now, there's a very specific hazard here called detonation. What causes it?
Detonation is catastrophic. It is the uncontrolled, explosive, spontaneous detonation of the fuel and air mixture before the spark plug even fires. It is caused by excessive pressure and temperature inside the cylinder.
When does that usually happen?
It often happens if a pilot is working the engine too hard, having the throttle, or manifold pressure, jammed wide open while the propeller RPM is set too low. The air gets trapped in the cylinder too long, overheats, and detonates like a bomb, which can shatter the piston head.
So, if I'm flying and I need to change my power settings, how do I sequence my levers to avoid creating those detonation conditions?
The examiners demand you know the sequences. When you want to increase power, you must follow the acronym MRT. First, enrich the mixture M to cool the cylinder. Second, increase the RPMR to get the air flowing faster. Finally, push the throttle T forward to increase manifold pressure. Mixture, RPM, throttle.
And when I want to descend and decrease power?
You reverse it, TRM. First, pull the throttle T back to reduce pressure. Second, reduce the RPMR. Finally, lean the mixture M. If you push the throttle forward before increasing RPM, you spike the pressure while the engine is turning too slowly, and you risk detonation.
Okay, that's pistons. Now let's contrast that intermittent, violent explosions in a box design with a gas turbine engine.
While a piston engine has intermittent combustion at a theoretically constant volume, a gas turbine is a continuous process operating at a constant pressure. It is essentially a highly controlled, never-ending blowtorch. Air is continuously sucked in, compressed, mixed with fuel, ignited, and blasted out the back.
The thrust equation here is Isaac Newton in his purest form. Thrust equals the mass of the air flowing through the engine multiplied by the difference between the exit velocity and the entrance velocity. You take a huge mass of air and you accelerate it backward. The hottest part of this entire process is directly inside the combustion chamber.
Now, a very common and difficult ATPL focus is the turbine section itself. This is the windmill at the back of the engine that extracts energy from the hot exhaust gas and uses it to spin the compressor at the front. There are two main aerodynamic designs for these turbine stages: impulse and reaction.
If I'm studying this is where my eyes glaze over. Walk me through the physics so I don't fall for the trap.
Let's look at an impulse turbine stage first. Every stage has two-part stationary guide vanes called the nozzle and the spinning rotor blades. In an impulse stage, the hot gas first squeezes through the fixed nozzle. The nozzle is shaped to accelerate the air so velocity increases.
Okay.
As velocity goes up, physics dictates that pressure and temperature must decrease.
Okay, so coming out of the nozzle velocity up, pressure and temp down. Then it hits the spinning impulse rotor.
Right. An impulse rotor blade is shaped like a simple bucket. The fast-moving gas slams into the bucket, physically pushing it, transferring its kinetic energy to the wheel. Because it gave away its energy, the velocity of the gas decreases.
What about the pressure?
However, the space between the blades does not change shape, so the pressure and temperature remain constant across the rotor.
Got it. Impulse rotor velocity drops. Pressure and temp stay constant. What about a reaction turbine?
The nozzle behaves exactly the same velocity up, pressure and temp down. But a reaction rotor blade is not a bucket. It is shaped like an asymmetrical airfoil.
Which means it's generating aerodynamic lift, like a wing.
Exactly. And because of the shape of the blades, the gap between them actually converges, acting like a secondary nozzle. So as the gas flows through the spinning reaction rotor, it continues to expand and accelerate. Therefore, inside a reaction rotor, velocity actually increases, while pressure and temperature decrease even further as the gas expands.
That is a phenomenal distinction to understand. Impulse rotor gas slows down, pressure stays the same. Reaction rotor gas speeds up, pressure drops. And finally, what about the exhaust cone at the very back of the engine?
Here is a major misconception that traps students. The main function of the turbine engine exhaust unit is not to accelerate the gas to create thrust.
Wait, really?
The main function of the exhaust is to straighten the swirling flow and extract the remaining pressure energy from the gas, carefully balancing its pressure and velocity to match the outside atmosphere, preventing violent flow separation and drag.
Okay, our engines are running smoothly. We are rolling down the runway, taking off, and climbing to 35,000 feet. We are entering an environment that wants to kill us. Section 6, Survival Systems. Let's start with keeping the passengers breathing. Pneumatics.
At high altitude, the outside air is too thin to breathe. So we pressurize the cabin to a differential pressure of about 7 to 9 psi above the outside atmospheric pressure. To get that massive volume of air, we bleed it off the engine compressor.
Bleed air. But I notice a weird quirk in the syllabus. Bleed air is technically taken from the high-pressure compressor of the jet engine, but the outline specifically notes it is drawn from the low-pressure stage of that HP compressor. So technically, engine bleed air is not considered high pressure. Why wouldn't we just take the highest pressure air available right before the combustion chamber?
Efficiency. The air at the very back of the compressor is incredibly highly pressurized and brutally hot. If you steal that air, you rob the engine of a massive amount of thrust, and you'd have to use huge, heavy heat exchangers to cool it down enough to pump into the cabin.
Ah, so it's a trade-off.
Yeah. The air from the early lower pressure stages of the compressor is warm enough to prevent ice and pressurize just enough for the cabin without severely degrading engine performance.
And we use that hot bleed air to melt ice on the engine cowlings and the wing leading edges. But before we melt the ice, we have to know it's there. The exam tests the historical evolution of ice detectors.
That's quite a timeline. The most basic is the hot rod detector. It is literally a small metal probe sticking out of the fuselage, visible from the cockpit window, with a floodlight shining on it. The pilot just looks out the window to see if ice is physically building up on it.
A bit primitive. Next is the rotor detector.
Here, a small serrated wheel sticks out into the airflow, constantly spinning. If ice builds up on the wheel, the aerodynamic drag increases, the torque required to spin it spikes, and that triggers a warning in the cockpit.
Then we have the pressure differential, or Smith's detector. It's a hollowed tube facing the wind with tiny holes in it, measuring ram air pressure. If flying in icing conditions, those tiny holes freeze over instantly. The pressure inside the tube drops, triggering an electrical switch and the alarm.
And finally, the modern standard on airliners, the Rosemount detector. It is a small probe that vibrates at a very specific, high ultrasonic frequency. As ice builds up on the probe, the physical mass of the probe increases.
Which changes the vibration.
Right. More mass alters the natural vibration frequency, which the computer detects instantly, triggering the anti-ice systems.
The examiners want you to know all of them. Now, there is a very specific silent threat called the cold-soaked wing. Explain what happens here.
Imagine you fly a transatlantic flight. You are at 38,000 feet for 8 hours. The air outside is minus 60 degrees. The jet fuel inside the wing tanks essentially turns into a giant, thousands of gallons block of sub-zero ice water. When you land at your destination, the aluminum wings are deeply cold-soaked.
So you're parked on the ramp in London. It's 10 degrees Celsius and raining.
Exactly. If the ground air is humid, that moisture hits the freezing wing and instantly sublimates into hoarfrost. If it is actively raining, the rain hits the wing and freezes into a sheet of clear ice. Both will completely destroy the aerodynamic lift of the wing on your next takeoff.
They use a clever operational trick. They will often fuel the tanks right after the last flight instead of waiting for the morning. The fuel coming out of the underground airport tanks is relatively warm.
Oh, that makes sense.
Yeah, by pumping warm fuel into the wings, it warms the internal structure from the inside out, preventing frost and clear ice from forming overnight. And for visibility, we have to keep the windshield clear of ice. We use that heavy-duty AC power we talked about earlier. Specifically, three-phase AC power is run through a conductive film embedded right inside the glass. It aggressively cycles between 18 degrees and 35 degrees Celsius.
And this doesn't just melt ice. Keeping the glass warm keeps it pliable, so it is less likely to shatter if you hit a bird at 300 knots.
Moving to rain, large aircraft do use wipers, but they also have rain-repellent chemical systems. The key fact here is that this fluid is intensely hydrophobic. It makes the water bead up and blow away instantly. However, pilots must only spray it in heavy rain. If you spray it on a mostly dry windshield, it smears into a thick, opaque paste that completely ruins forward visibility.
It's a mess.
Let's talk more about that jet fuel. There's a massive emergency procedure. Pilots must know fuel dumping. If an airliner takes off at maximum takeoff weight, it is incredibly heavy. If an engine fails immediately after liftoff and you have to return to the airport, you are likely way above your maximum landing weight. If you smash the plane onto the runway at that weight, you could snap the landing gear or structurally fail the wings.
So you must dump fuel overboard to lighten the ship. The exam wants you to know that dumping fuel specifically minimizes the wing G-loads upon landing.
And what exactly are we burning? You must memorize the fuel specifications. The standard civil fuels, Jet A and Jet A1, have a relatively high flash point, the temperature at which they emit enough vapor to ignite, of 38 degrees Celsius. Jet B, which is used in extreme cold weather, is much more volatile, with a flash point of minus 20 degrees Celsius.
Crucially, you must know the freezing point. Jet A1 freezes at minus 47 degrees Celsius. When fuel starts to freeze, it doesn't turn solid all at once. It forms wax crystals that clog the fuel filters, starving the engines of fuel. Pilots must constantly monitor fuel temperature at high altitudes to ensure it stays safely above that minus 47 degree mark.
Finally, oxygen. If that bleed air system fails and we lose that 7 to 9 psi of cabin pressure, the air gets thin very fast. If the cabin altitude exceeds 14,000 to 15,000 feet, the passenger oxygen masks drop automatically.
The oxygen for the crew is stored in high-pressure gas bottles. A critical safety feature for these bottles is the thermal relief valve. If there's a fire, the heat will cause the pressure in the oxygen bottle to spike dangerously.
Right.
To prevent the bottle from detonating like a bomb and feeding pure oxygen into the fire, max pressure bleeding is handled via a safety plug. The plug melts or blows out at a specific pressure, safely venting the gas overboard through a port on the side of the fuselage.
We have covered an immense amount of ground. From the torsion box in the wing, to the Q feel of the hydraulics, through the star-connected AC electrics, the reaction turbines, and all the way to the freezing point of Jet A1. How should a student mentally organize all of this for the exam?
If we connect all of this to the bigger picture, it really shifts your perspective. When you sit in the cockpit and look at the overhead panel, you aren't just operating independent machines, you're managing a fragile ecosystem. The heavy fuel in the wings structurally fights the aerodynamic bending of the spars. That same fuel cools the hot hydraulic oil.
Wow, yeah.
The mechanics of the turbine generate the AC electrics, which run the pumps, which power the irreversible flight controls. The bleed air fights the ice and keeps the passengers conscious. If one single system fails, the symptoms will cascade across the entire board. The ATPL exam tests your memory of these specific numbers and limits, but true airmanship is seeing how they are all breathing together.
That is an incredible way to look at it. To our listener preparing for their ATPL instrument exam, you have got this. We've built the skeleton, we've pumped the hydraulics, wired the electrics, fired up the turbines, and brought the systems to life. Next time you look at a commercial airliner sitting on the tarmac, don't just see a rigid tube of metal. Ask yourself, are you seeing static engineering, or are you looking at the pulse of a mechanical organism? Thanks for joining us on this deep dive. Keep that curiosity alive, and good luck on the exam.